All right, so here's an example of a problem that you might run into in our LO that we're testing on work and energy, when you have to either use conservation of energy or the work energy theorem. So in this problem, we have a little toy car. Well, it's not so little, it's 5 kilograms, but anyway, it's a toy. It's going to slide down a frictionless ramp, and it's going to hit this spring, and the spring has a spring constant of 4.9 kilonewtons per meter. And we're going to say, what if the spring compresses a maximum compression of 22 centimeters? So we're imagining that like the spring looks like this when the car is here, and this distance that it moved is 22 centimeters, and it's coming to a stop. That's why they say a maximum compression. If that's the final location of the car, they want to know what would be the height that it was released from. So this is question A. In question A, because we don't have friction, energy is conserved. So I like to just do initial energy equals final energy. Now, because the car was released, it didn't have any kinetic energy initially. It wasn't moving. We just let it go. Its initial potential energy is mgy. When the spring is compressed to a maximum amount, the car doesn't move anymore, so no final kinetic energy, but this time we have potential energy at the end in this compressed spring. So this is our expression, and we're going to solve for y. Now, some things we have to be careful of. The K was 4.9 kilonewtons, so it's 4.9 times 10 to the third. And the compression was 22 centimeters. We have to change that into meters. So there were two values here. We had to be careful about the units, the K and the X. Divide by the mass. The mass of this car was 5 and 9.8. This gives us a Y value of 2.42 meters. So it was pretty high, but that's okay. In part B, we're going to change it up a little bit just to see how we would do it if there was some friction. So right here, what they're saying is that there was a little rough patch in here that was about 10 centimeters where there was frictional force. That means that energy is not conserved. I like this approach where we look at the change in energy, and in this problem, it's due to work done by friction or energy dissipated by the frictional force, and so this is how we would look at it. If energy was conserved, this side would be equal to 0 because there would be no change in energy, but because of the friction, there is a change in energy. The change is negative because we end up with less energy than we had originally. Okay, so I put in some things. The change in kinetic energy, of course, is the final minus the initial. Same thing for potential energy. Our friction is expressed as mu k times the normal, and the normal will be mg because this is happening when the car is on the flat part of the track. So our final kinetic energy is 0. Just to remind you, what we're trying to figure out this time is how much will the spring be compressed. Our expectation is going to be less than 22 centimeters because it won't have as much energy when it hits the spring. For this problem, we're going to assume that the initial y value is the same as the one we found in part A. So a lot of math here, and I just kind of ran out of room. It looked like a mess. When I saw for x, I get 0.218 meters. It's a very small difference, but it is a difference nevertheless. So it really compressed just a millimeter, 2 millimeters less than it did without the friction. But that's how we would do it. So hopefully it's helpful.